Welcome everybody to our 7th lecture. Today I'm going to talk about boosting. So last week, Louis introduced decision trees and the concept of bagging. So bagging is take a random sample from a dataset, use this subset of data to train a model, and then repeat this many times so you have a bunch of models that you can average or for classification tasks, we usually take the majority vote. And so, but we also learned that these models trained on random samples of a dataset may be highly correlated. So that means not just the structure is similar, but their predictions. Yeah? And so bagging doesn't help much to reduce the variance. And if you don't know and don't remember what variance was, go back to the video on model validation. So just to summarize, if you have, if you do cross-validation on this one sample and you see it sometimes performing very well and sometimes very poorly, then this means you have a high variance. Yeah? And you typically want to reduce variance, which you can do by combining classifiers. But if they are correlated, then that doesn't help in reducing the variance. And so then Louis introduced you to random forests, which in their construction use random variables. And by doing that, help decorrelating those single individual classifiers, and thereby, reducing variance, improving performance. And the last step in this development of ensemble models, I'm going to introduce you to boosting. And by the way, I should note that bagging or boosting do not require the individual models to be trees. Obviously, random forests do, but bagging, uses any kind of predictor and averages them. We can use, for example, neural networks to improve the performance from a single individual network to an ensemble of networks. And we can also use boosting in the same way. And today we're going to learn how this works. The underlying idea here is really that our individual predictors get assigned a different or a particular weight. Yeah? So in the ensemble, in the committee that we will try to form, each predictor has a certain weight. Huh? And these predictors can be seen as like experts that have been trained to be good in performing, on specific parts of the data sets. Yeah? They may have been trained to focus on individual samples in the data set that were identified previously as specifically hard to predict. And so boosting is the combination of classifiers. In boosting, usually tends to use very simple classifiers, many of them. And the only requirement that we have for these simple classifiers is that they are better than chance. Yeah? So they should provide some information as to which features of the data are relevant. But really they don't need to be, so the single individual predictors don't need to be excellent. Yeah? They just need to be okay. Now, let's compare bagging and boosting. bagging, again, takes a subsample of your data, trains a model, and then repeats that many, many times. And so what you end up with is a set of predictors, F1 through F whatever, M, and we combine them by, for example, averaging. And the final predictor, capital F, just evaluates them in parallel and then puts their output together. Now, the performance of each individual predictor doesn't have an effect on how we, sample the next time, or doesn't influence the result of the learning process of the consecutive models. And that's exactly what we do in boosting. So here we introduce two parameters here. One is the weight W of each individual data point, I, and each of these individual predictors is also weighted in the evaluation of the final classifier F, or capital F. So what we just do is we sum all these outputs up, and then each of these outputs carry a weight alpha. And the final predictor F just returns a 1 or a -1. So yeah, it's like a bipolar output here. Okay, and so in boosting, what we want to do, and we'll see how this works in the following, we start by a uniformly weighted data set and feed this into the training process of F1. And now, evaluating how F1 performs, we identify those samples that were hard to classify or were wrongly classified. And we increase their weight such that whatever F2 will learn will look differently. And so we repeat this process. We look at how bad or how good F3 was given the previous weighting of the data. And then we train a new model that takes into account an updated weight or weighted data set. And in the end, so let's say we have completed the boosting process with 5 classifiers, F1 through F5. The combination here then is also determined by this weighted sum. And this weighted sum has also something to do with how well each of these classifiers performed. Okay, so boosting is a family of algorithms, and we're going to present to you AdaBoost. I think probably the most well-known algorithm in this family of algorithms was proposed by Freie and Shapiro in 1996, I think. But this is here the citation everybody cites, so it has been cited more than 20,000 times. So this is a really popular thing, and it's really simple. So it has basically only 4 steps here in this inner loop. We first initialize, our data weights, and then we train many classifiers. And after this, we calculate the classification error. And by the way, you can use boosting for regression tasks as well. But let's just for now look at classification. So we compute the classification error, and then this error is used in computing the classifier weight, so the coefficient in the sum, and the sample weights. And then we do that many, many times, and then boom, that's our classifier. Good. Let's just talk about how we want to use the classifier error to determine those model coefficients alpha m and the data point weights wi. So I said we're going to look at how hard a sample was, and this hard is evaluated globally. Yeah? So we don't look at whether a point was close to a decision boundary or far from a decision boundary. In a way, this point here would be much more, difficult to classify, especially for a linear model. No, we will look at how this model performs on the data set. And so both of these points will, be considered equally hard because this model misclassifies them. And the rest is correctly classified. So how do we calculate our error? So EM, which is the error of the mth classifier, basically looks at how many times the prediction of the model was wrong. So yi are the given labels of our data set. And so I of this expression just means if this is true, so if the label was unequal, not equal to the prediction, or the other way around, right? Then this evaluates to 1. So in the sum, so in the sum here, we add up all those weights that correspond to those data samples that had been classified incorrectly. And then we divide this by the sum of all the weights to normalize the error. And this is, basically another way of saying this. So sum up all the weights for those samples that have been misclassified, and then divide it by the sum of all weights. So we can imagine here W to be a vector of all the weights, and since they will be positive, the L1 norm is just summing these guys up. Now, let's think of an array of weights like this, and we have identified one of our samples that has been misclassified. And in the following, we'll look at how we can increase the weight of this data sample, and maybe looking like that. But since we are normalizing the error, the influence of other samples, those that have been correctly classified, is diminished indirectly because we are normalizing everything to be sum 1. Yeah? Good. So the first step after obtaining a value for the error, we need to update our alpha m, or we need to define it. And in AdaBoost, we use this expression. So the logarithm of 1 minus the error divided by the error. And so 1 minus the error means we get large values if there's no error. Yeah? And so taking the logarithm means we can squish this a little together and get this nice curve. And let's see what this curve actually means and why this is a good way of doing it like that. So our error, lives between 1 and 0, right? So 1 means that all of our samples have been misclassified, and 0 means all of our samples have been correctly classified. Now, an error of 0.5 in the very first classifier, because then we have a uniform distribution of data point weights. That means the classifier just randomly, assigned class 1 or a class -1. And that's a classifier that doesn't help us much. So if we, go to lower errors to this direction, that obviously is better. Yeah? But also a classifier that has a higher error is good. And why do you think that is? Well, if a classifier is always wrong, it means it has understood already the structure of the problem, but it's just a sign problem. So we could do exactly the opposite of what this classifier would say, and then be always right. Yeah. So an error of 0.5 is the worst, and then we want to be either here or either here. And when we are at this, point in the error, we just flip it by assigning it in negative alpha, right? So remember, the alpha here is multiplied on the output of the classifier. Now, obviously, we assign a 0 weight to those who are in this region of being close to or on 0.5, and also everything that is below 1 really has a small effect on the output. Has an effect, but rather a small one. Yeah. Good. Now the last point. So the previous slide told us, okay, how do we obtain a weight for the classifier? Now, how do we reweight our samples? And so the paper of AdaBoost states this. So our WI is updated by just multiplying e to the minus alpha m, so that's what we computed on the last slide, times yi times f of xi. Now, this multiplication here is something positive if the sign of the prediction and the sign of the label agrees. So they're either positive or either negative, and then we have a positive sign here. So e to the minus alpha is the factor that we use to scale our previous WI. Yeah? And if the sign of prediction and label disagrees, then this will become e to the alpha. And so this is something large compared to e to the minus alpha. Is, it's equal to 1 over e to the alpha, so that's small. Yeah? So we increase the weight for those samples that have been misclassified and decrease the weight for those that have been correctly classified. Yeah? And for those that have been incorrectly classified, for example, those 5 here, we will obviously increase the weight, and then the next classifier will try to accompany them into its into its decision boundary, such that they are on the correct side of the world. And sometimes that's not possible. For example, here the red one will probably then in the next iteration increase further its weight, and also those red ones here. But they had, so those green guys here have been correctly classified, so that's good. To summarize on one slide for you to be able to learn for the final or for the midterm midterm exam. Just a summary of AdaBoost with how you compute the error, how you compute the alpha classifier weights and the WIs, the sample weights, and how you compute the ensemble model. Now, this is an example that Luis just did. If we use decision stumps, so those are trees that only ask one question. So, is the data point this or that? Yeah. So it takes one dimension from the data. So here the second dimension, and asks a data point: are you above or below that threshold value? And if that's a pretty simple classifier. Yeah? And using only one obviously doesn't give us good results, because first of all, it's just a linear separation, and then we don't even have a way of rotating this decision boundary. It's parallel to the axes. Yeah, so those points here and here and here and here, they are misclassified, and then they are in the boosting process regarded as especially important. And then if we then take the second stump, then this decision boundary here is introduced, and we'll then be able to correctly classify this arm of the distribution. And then the more we take, the more complex also our decision boundary gets. So as I said, boosting also works in regression tasks, and you will find in scikit-learn a couple of data sets that you can play around with. And to show you the power of boosting, or especially AdaBoost here, we looked at the performance of an ensemble of that many predictors, so from 1 to I think 30. And we see that especially here in the beginning, AdaBoost performs very well. At some point, it even overfits. Yeah? So I think this probably indicates overfitting, while bagging and random forests don't really show us any improvement over the number of predictors that we integrate here. And in classification tasks, so for example, the breast cancer data set in scikit-learn, we'll pretty much see the same picture. So AdaBoost performs best, bagging the worst, and random forest right in the middle. Yeah? And these results may look a little differently, using different base classifiers. But I think this is what we introduced you to in the very first slide. So you can expect this kind of behavior in pretty much all the problems, using many of different base classifiers. So in the following, we're going to look into a little bit of a theory. So if you're interested in theory, stay. If you're not too much, then maybe go get a coffee, or forward to the next lecture. In the next couple of slides, I wanted to show you that AdaBoost doesn't, magically came up with the rules to update the weights for the data points or the alphas, the coefficients for the base classifiers. They were defined and chosen such that the model weights minimize a so-called exponential loss function. Yeah? So this loss function is just the sum over all data points of e to the yi minus yi times capital Fm of xi. And this classifier here isn't the final classifier like we had previously with sign of the weighted sum. It's just the weighted sum. Yeah. And up to the last classifier m. So alpha m is here the coefficient of the last Bayes classifier, small fm, and it's chosen to minimize the exponential loss. And why that is, I'm going to show you in the next slides. First of all, we have to understand what those weights, the data weights, are. So our weight wi for the mth iteration is just the weight of the previous iteration times e to the minus yi times alpha m minus 1 times fm minus 1 of xi. So this is the rule that I just copy pasted from the previous slide. So this is exactly what we do to update the new weights for the then last iteration. But these wi in the m-1 iteration, these could be expanded into the entire sequence starting from 1. Yeah, so the next step would be wi to the m-2 times e to the minus y alpha m minus 2 times fm minus 2 of xi, and then the last e term here is taken from above. And then you can do this many, many times until you hit the 1, and then exponential functions can be rewritten like a product of e functions are the e function to the sum of the exponents. Yeah, and then you take this minus y out of this whole sum, and then you will see that in the sum, this is actually just the sum of all the Bayes classifiers, which we called capital F m minus 1. So the weights are basically just a sequence or the product chain of exponential losses. And this becomes important on the next slide, and that's why I put this border around it. So let's get to the proof. We start with the equation of the loss that we just introduced a couple of slides before. And then we look at capital Fm, which could be just rewritten as the previous f m minus 1 plus the final Bayes classifier, small fm, times its coefficient alpha m. And applying the same trick as we did in the previous slide, we could rewrite this exponential function with the sum here, by multiplying this y on here, and then rewriting this as a product of two exponentials. And since this first exponential on the previous slide was identified as the weight of the mth iteration, we can rewrite this like this. And now we want to separate all these terms in the sum such that we have one sum only for those samples that have been correctly classified. So small fm was equal to the label. If they had been equal, they have their product has a positive sign. So what remains is only wi m times e to the minus alpha m. And for those predictions that are not equal to the label, the product of those two numbers has a negative sign, and so multiplied by this negative sign results in this term. Now, to minimize this loss term that we've just wrangled a little bit around, we need to do what we always do. We take the derivative and we set the derivative to 0. And then we try to come up with an expression for alpha. So let's do exactly that. We start with this, and the derivative of this with respect to alpha is just, putting these alphas in front of those, or well, in front of these parts of the sum. And we can even drag these out of the sum and then move this whole sum to the left of the equation. But since both parts of the equation have the same weight, we can just cancel them. So we're getting close. We can simplify these two terms a little more. So the sum of all the weights, where the predictor was correct, is basically the error of the predictor, but inverted, right? So this was either 0 or 1 or something in between. So 1 minus the error is the rate with which the predictor was right, and then we multiply it by the sum of all these weights, and that's exactly this part. And for the incorrect predictions, we could just take the error EM. And now let's write this down again. So and maybe get rid of those e functions by taking the logarithm. Yeah. So then this remains. So minus alpha m plus logarithm of 1 minus e equals alpha m plus the logarithm of e. Yeah. So we could add 1 alpha m here, and then subtract this logarithm over here, and then applying a logarithm rule could be rewritten as logarithm of 1 minus e over e. Yeah? So alpha is equal to logarithm of this term divided by 2, which is exactly what we introduced it in the very beginning. Now you see, sometimes you'll see this, equation for alpha, of this rule in the description of AdaBoost without the divided by 2, which it doesn't really matter, because those alphas are the coefficients for those base classifiers, and if they all have the same constant here, that doesn't change the sign, in the final classification. So enough of the theory. This was AdaBoost. We haven't yet talked though about how to use the weights in the training of the weak classifiers, and we haven't yet talked about any practical application. So that's why we decided to show you a very popular, famous algorithm, proposed almost 20 years ago. So I hope you enjoy. So the algorithm I'm going to talk about today is called Viola-Jones, because of its inventors, Paul Viola and Michael Jones. Published in 2001, so 19 years ago. It proposed using very simple features that then are boosted with AdaBoost, and a couple of tricks that I'm going to talk about in the following slides, to then eventually detect faces or other objects in images. And since 20 years ago, the computers were not as strong as the ones we have today, those tricks helped a lot to speed up the process. And though training took quite a while, very similar to the models that we train these days. So before we start, let's do a small experiment. I'm not going to tell you what kind of objects we're looking for, but the question I have for you, I will increase now the resolution of this image, and you tell me when do you think you would recognize what is on the picture? Let's go. So obviously it's a face or is a person here. I don't know, maybe second stage or third stage. So I think I would probably recognize that this is a person at stage 2 or 3. Now, if you squint your eyes, that makes things a little easier, and I can even see who that is. Do you? So this is Barack Obama. So, bottom line, we need not many pixels to identify whether a face or a person or an object is in the video or in the photo. But of course, to identify which object or which person it is, we may need much higher resolutions. So if you just wanted to detect faces, to maybe autofocus the camera or to, I don't know, anonymize faces in public videos, we would just need to detect simple patterns. Yeah? So Viola and Jones demonstrated that face detection is possible using very simple features. Yeah? So the weak classifiers, the base classifiers in the boosting part of the lecture now become visual features, and we're going to see what these are. And it was, I think, one of very, very few algorithms that ran in real time. So real time means 15 frames per second on images that are, very, very small for our standards today. But because it could run in real time, it had been integrated into mobile devices, cameras and all these things to detect faces. And there are 3 key ingredients, and we're going to talk about all of these. You know about AdaBoost, but first we're going to look at a data structure called integral image that speeds up the evaluation of these simple features. And so then AdaBoost is used to determine the coefficients of these simple features in the final classifier. And also I'm going to show you how they propose to reorganize the evaluation structure into like a cascade of strong classifiers, starting from strong classifiers with only few simple features up to more complex, more costly classifiers. All right, let's start with what are the simple features here. So, looking at an image of a face, or maybe use my face, you see that there are bright areas and dark areas. Here maybe my beard and my hair, not as dark anymore, but anyway. And we have 3 different kinds of these simple features. One with 2 rectangles, one with 3 rectangles, and one with 4. And these rectangles are matched against the image, right? So, for example, one basic feature in faces is that the cheeks and maybe the nose are brighter than the eye area. Yeah. Or look at the middle feature here. That the nose typically is brighter than the eyes, and then you can think of those diagonal features to kind of contribute to the round shape of faces. So how do we evaluate these features? we basically sum up all pixel brightness values in this positive, in this bright region, and subtract the sum of these brightnesses in all these dark regions. So you can think of this first part is high when those pixel values are bright, when those pixels are bright. So if this white region is here in the top, we sum up only low values. So convention is black is something around 0 or close to 0, and white is something close to 255 if we have 8-bit images. So if this would be on a dark spot, this first sum would be low, and if it's on a bright spot like here on the nose, this first sum would evaluate to something high, to large values. Now, and this last part here should evaluate to something very small to have a high output of this feature. And so if those dark spots are, those dark rectangles are on dark areas on the face, this penalty term here will be small, so it's a good fit. And now think about exactly the opposite. So if this white area here would be on a dark area in the face, and those black boxes on bright areas, then this sum, this subtraction would evaluate to something negative. Now, even on a 24 pixels by 24 pixels image, we can find a lot of different locations for these simple features. So 160,000 given those simple features that I showed you. And we do have a lot of training images, so we need to evaluate these many times to see which one is good on many training images. So we need something to speed this up. So the integral image here, XX, is just the sum of all pixels from 0, 0, and in images we typically start in the top left corner and not in the lower right left corner. So from 0, 0 to our target pixel yi, sum up all those pixel brightnesses in there and put this into this new matrix that's called integral image. And this can be computed in only one pass over the input by looking at two different data structures. One is the integral image itself, and one is something that can be computed in one pass over an image line, a row in this matrix, So, and this line here is called S. So we just sum up all the pixels that we visit and write this in this array of sums. And now once we've completed the sum, the integral image entry at this point can be computed by looking up, which gives you the entire sum the entire sum of the image in this region, and then of course you have to add this line here. Now, if we now want to evaluate such a rectangular feature, this three rect feature, we can do this with only a few accesses to the integral image, and we don't have to iterate over the image again. We just look up the integral image at a couple of positions. All right, let's do this. So in order to get the sum of pixel values in this region, we need to look at, well, this point in the integral image, which gives us the area here. Yeah? So the sum of all pixel brightnesses in this area A. We can look up the integral image at this position, which gives us everything in this region here. Yeah? So region A plus B. And we could look up this position in the integral image, which gives us the entire region here. And of course, this corner gives us A, B, C, and D. Now, in order to calculate the sum that only corresponds to D, we add the integral images entry at this corner, which gives us the entire pixel sum, and this area, and then we subtract this area here and this area here, given at these coordinates in the integral image. Yeah? So why do we add this region A? Well, because we subtract it twice. Yeah? So once it needs to be subtracted once because it's included in this, in this value here in the integral image, and then that's why we add it another time here. Yeah? Good. The cool thing now is that evaluating a feature costs constant time. Yeah? So we don't have to iterate over all those pixels again. We just access the integral image 4 times and add these values up, and boom, we have our feature value. Yeah? And building the integral image is also not as expensive as we think. It's just running over all pixels once. So if we have a big image with a couple of phases in there, we just compute the integral image for this for the scene, and then we can evaluate the feature locations in constant time. Now, let's come to the process of defining which of these features are the best. So again, we have, for a tiny image of 24 by 24 pixels, around 160,000 possible features. So all the possible locations of all the possible kinds of features. Now, let's say we wanted to evaluate, we wanted to extract the 200 best. Best means, using these, we can, detect faces with lowest error. So the solution, obviously, and you know that, is AdaBoost, or is boosting those features. And the paper uses a little bit of a different notation here, and that's why we introduce this here again. Previously, we had the small f's as our weak classifiers or base classifiers, and it changes to h, and they evaluate to 1 or 0, not 1 and -1. Yeah? It's a little different. Don't worry, doesn't really matter. And this weak classifier here has 2 parameters. One is so-called parity, and the second one is theta, the threshold. So if the function f evaluates with a number smaller than this threshold, then the output of the weak classifier is 1. Now, if we think of our possible values and the threshold being 10, you know, we might want to say it is a phase if we exceed the threshold, but sometimes we want to do it the other way around, and we want to say, well, no, if it's below a threshold, then it should be seen as a phase. Now, and that's why the parity bit is here, sorry, the parity sign is here. So P is either -1 or 1. So look, for example, if we had an f of x equals to 11 with parity 1, h would return would return 0, yeah, because 11 is not smaller than 10, but with parity -1 it is, and then it would return 1. Now the strong classifier is really again the sum over all of these given h's, and each of those h's have their coefficient, and you know, you can think of the final classifier has also a threshold that we can determine later, but now we can think of this as, you know, if the sum over all these weak classifiers evaluates to half of all the alphas, then we can consider this a phase. Yeah? But later we will see we can also tune this threshold here in order to control the number of false positives and true positives. Again, in this boosting process, we will look at samples that have been incorrectly classified as non-phases, or non-phases that have incorrectly been classified as phases. So let's say this blue region is the phase region, and the green region is the non-phase region. So we have two samples here, phases that have been classified no phase, and they are identified and increased in weight, similar to what we've learned in the previous slides. Now the classifier H2 then learns to classify them correctly as phases, and then we end up classifying these guys here as phases too, although they are no phases, and so we give them more weight, and then we continue this, and the final classifier looks similar to this and has learned the structure of the data. So boosting in the Viola-Jones paper is pretty similar to what you've seen before. There are two or three minor differences. Let's point them out. So first of all, we initialize the weights for the positive and negative samples separately. So positive, phases, and negative are non-phases. And we do normalize those weights, although this could be done in the original description of the algorithm as well. It shouldn't hurt anything. We do compute the error a little differently. So the hj is evaluated to 0 or 1. And so comparing it to the labels results in 1 if there's a misclassification. So the error is basically the sum of all the weights of samples that had been misclassified. Alpha, is the same as before, and now the sample weights are a little different. The sample weights are scaled by beta. We will see about what this is later, and only if only if they had been classified correctly. So EI is 1 if the classification was equal to the label. So if it's not, then beta to the 0 will be 1, so it won't change anything. Now, beta is this, so it's the inverse of what is in those brackets here of the logarithm, and that's basically just another way of writing e to the minus alpha. Yeah, you can write this down and see why this is true. So what we basically do is the same as in the original description. We multiply this by e to the minus alpha, but only for positive for correct classifications. So we decrease the weight for the correctly classified samples. And since we normalize the weights, this in effect increases the weight for all the others, for the incorrectly classified ones. All right. How we can determine which of those features are the best. And by the way, we haven't yet talked about the parameters of those features. So they are in a fixed position, and they evaluate fixed pixel regions, image regions. You know, sum the bright parts up and subtract the dark parts. And well, we haven't yet determined those two parameters, the threshold and the parity. So think of this feature here and a couple of samples we used to evaluate this feature. And you know, some faces could receive very low values, and some faces could receive high values, and also non-faces could, you know, have some values. Now, the question is, how do we determine the optimal threshold theta and the optimal parity p? So, you know, there are not infinite possibilities here. We only have n images, samples, that we use to evaluate f1. And so each of these numbers could be a possible threshold. Yeah? So for example, if we use 1, it would mean that we divide this field into a positive part and the negative part, or vice versa if we flip the parity. Yeah? So the threshold theta is has you know, at max n different values that we have to choose from, which is good. Yeah, so we don't have to search n in a huge space. So the goal here is now we want to minimize the classifier's error. Yeah, which is we have this one h, or it's called f here, and it's compared to the label of the sample, and if we have a misclassification, we sum up those weights. Yeah, and those weights are depicted here as the different diameters. So the idea is we are going to iterate through these values here, and each sample or each value that we visit is a possible threshold. And to be able to calculate the error that would correspond to this setting, to this threshold setting, we keep track of two sums. So the sum of weights of the positive samples in the left partition, that's what we call L plus, And L minus is the sum of all the negative sample weights. And stepping through this array of values, and at each position, testing a certain threshold, we have to add only the weights of those samples that are coming into this left set, into this left partition. So this could be either one sample into L plus or L minus, or if many of these samples had the same feature value, then we have to sort those few samples into the positive or the negative sum. But we add only few values. Yeah. Now, looking at this example here, at this partition, we could think of the threshold, or well, this would correspond to the threshold 1, and the parity, I think, -1. So all these samples to the left would be predicted to be no faces, or answer 0, and all these samples to the right here would be predicted to be faces. Now, those faces are incorrectly classified no face, and this no face would be incorrectly classified as a face. And the error thus is the sum of all positive weights in the left part plus all the negatives, and this is a number that we have because we normalize them, yeah, those weights to be 1. So this would include this weight, but also this weight, but this needs to be subtracted, and we have this in our L minus. Yeah? So the error that we're looking for, the quality of this feature, is L plus T minus L minus. So those are the parameter values here that I've just told you. And what if we switched this around? So what if the parity was +1? So all the features, or sorry, all the values, yeah, all the features that evaluate, all the samples that evaluate below the threshold, so are in the left part, they now have to be faces. So the error would be this green, this no face sample, and vice versa. The classifier would evaluate 0 if it's above the threshold. So then all those faces would be errors. And we do the same computation just by switching a little bit around those variables here. So we now consider, an error all those non-faces in the left part, plus all the faces in the right part, which is all faces minus all faces in the left part. Yeah. So in the end, we just compute L plus and L minus, and we do have already computed T plus and T minus. And we compute this number and this number, and then we know by looking at which is smaller, we already know the parity, the correct parity. Yeah. And so we go through this array of values, test in a way all different possible thresholds, and get the corresponding parity by looking at this minimum. Okay, so this is basically what we do. We have 160,000 weak classifiers, so those rectangular features everywhere in the image, and then we look at which one has the lowest error, and then we take this guy, give it a weight, re-weight those samples, and do this all over again. So we have a way to build a strong classifier. Now these classifiers are tuned to be in a fixed window, yeah, of 24 pixels by 24 pixels. And what do we do if we had a super large photo and had many faces in there? Well, obviously we take this sliding window approach, and it works like, you know, the name tells you already. We have a target window of 24 by 24 pixels, and then we test this position, whether it is or is not showing a face. So we slide this window further until there is a face, and our classifier correctly responds by saying 1, that is a face. Now, because of the variation in the training data, and maybe imperfections in the way we compute the value, or we set our threshold of the final classifier, we will get many detections around a face. And so what we could do is filter those out, or average those windows into only one in a post-processing step. So we will now get into something that's a little bit of a speed up, but it's also a very important part of the paper, and it's called a Cascade Classifier. So most sub windows, except in images like you just saw, but most sub windows in such an image are no faces, and so we have a lot of computation in there, looking at 200 or so features, even though we have accelerated their evaluation with the integral image. This takes time, yeah? And so the idea of this Cascade classifier is, hey, let's use a very simple strong classifier. Simple in the sense of it uses only a few weak classifiers, therefore it's very fast, and it doesn't reject any positives, but it does reject many negatives, although still 50% or so of the negatives are passed through, so are reported to be a face, but they aren't. So but this way we can reject many false or many non-faces early on, so that the more complex classifiers, those that are costly to evaluate, those with many weak classifiers, can be used only then when it's pretty sure it could be a face. Yeah? And this is how it goes. So, as I just said, we have a list of sub-windows, and this classifier Cascade now rejects sub-windows, and we know that most of them are non-faces. Yeah? So it says false correctly, and it passes down the cascade only those samples that are hopefully positives. Yeah? In this way, we can increase detection speed because those first classifiers use only a few weak or base classifiers. Now, we are going to use false positive rate and true positive rate. That are things that had been defined earlier in, I think, the fourth lecture, in the model validation lecture. And so that basically means, all the true, so the number of true or false positives divided by the number of samples. So that's a number between 0 and 1. And then we can look at each of these stages with their false positive rate or true positive rate, and to calculate what the final classifier, so running through all those stages, would produce in terms of false positive rate or true positive rate. This is just multiplying these rates together. Now, remember we had the final classifier that is just the sum of the weighted h's. Yeah? So the alpha I times hi. And summing all these guys up, then in the end we compare this, whether this sum is larger than a certain threshold. Now we still have control over this threshold. Lowering the threshold means more samples are classified to be a phase, although this could also mean they are falsely classified as phases. So we increase false positive rate, but also the true positive rate. So this false positive rate isn't what we want to increase, but we do want to increase the true positive rate. And if we can also increase the threshold, it means fewer and fewer samples are classified as a phase, then we can turn down the true positive rate or also turn down the false positive rate. Yeah? So let's look at the details of how to build such a cascade classifier. We start by defining targets for how much false positives we want to exclude from stage to stage, how many true positives we are allowed to lose from stage to stage, and a total false positive target that tells us when to stop. So we initialize the false positive rate for the current stage and the true positive rate for the current stage to be 1, and an index of the stage to be 0, and then we run this program. So let's get an understanding of what this program does step by step. So the outer while loop continues this program while the false positive rate is still below, above this target false positive rate. Yeah? So if we go below this, maybe under 5% or so, we'll break this whole training process and we're done. But as long as we are worse than that, we continue. So that's the stage identifier, is set to 1, or incremented by 1, and I is here the number of weak classifiers in each of these stages. We start with an initialization, and also the false positive rate. So the proportion of samples that is wrongly classified to be a phase is the same as the previous stage, because we didn't yet do anything. Now, the second while loop looks at the false positive rate and whether it is below a threshold that is maybe 90% of the previous false positive rate. Yeah? So remember, we want to get below a target, so we want to sort out false positives. So we'll train a better and better classifier to be then able to say, okay, we have rejected another 10% or 20%, and then we can get to the next stage. So having a high goal of rejecting lots and lots of samples isn't the way we go here. Because this comes at a cost of adding many weak classifiers. Yeah, and we want to do this step by step. Okay. So n is the number of weak classifiers, is incremented. So we will train a classifier Ci with that many features. So we start by 1, and then we'll evaluate this on the validation set to get a false positive rate and a true positive rate. Yeah? And so since Ci has this, starting threshold of half of the sum of all alphas, we can still tune this threshold to produce more positives. So we decrease the threshold. So we increase our true positive rate. Yeah. So, and we stop doing that until the true positive rate measured is larger than the old true positives diminished by some percentage. Yeah? So that means we have to at least pass down the cascade that many positives. Yeah? So D could be 99% or 95%. Yeah? We don't want to lose those positives. Yeah? And so we'll keep doing this until the threshold at that point, not just produced more true positives, but also more false positives, and this condition isn't met anymore. Yeah? And so this means, okay, we have rejected a lot of stuff, but by keeping the positives in also comes at a cost of keeping the false positives in, and so we need to stop here. Yeah? Good. Think about this a couple of times and ask questions in the Q&A session. So to summarize, and I think this is the longest lecture we had so far. Boosting is very powerful, and we showed that in one of those previous slides how it compares to bagging and random forests, for example. But boosting oftentimes is used to increase the performance. Bagging, though, is used to reduce variance. So it's not the same kind of goal those two methods actually try to achieve. Boosting often suffers from overfitting. Yeah. All right. So Viola-Jones, in the second part of this video, introduced you to those simple rectangular features and the integral image to evaluate these features. A slightly modified version of AdaBoost to build strong classifiers, and also a way of building a cascade of these strong classifiers to boost your runtime, because you reject a lot of windows to be negatives, and then use only those strong classifiers, the complex classifiers that have many of these weak features than later in this cascade. All right. So this was the 7th lecture. I hope you enjoyed it. I hope you collected a couple of questions for us for next Monday. So enjoy the weekend. See ya.